First of all, thank you, Ernesto. I'm Tomer Ganor. I'm a tech lead at Sartora, and I'm going to show you how to use CVL to improve security in Aave and protocols like Aave. Okay, let's start. So, what is even CVL? So, CVL is a language that has a syntax that is Solidity-like, to help developers write properties for their code. That should be more intuitive for developers because it's similar to Solidity. Why do we use CVL? We use CVL to write tests that find all of the states, all of the possible edge cases that might happen, as Ernesto said, and it don't let us to avoid some state that we'll think about, and then we know that we are covered. How do you do it? We formalize the property in CVL. We write it in CVL rule, as we will see right now. And we run with the code, the Solidity code, we run it through our prover, and then we get a result from the prover. The results might be one of two results. Either we get verified, which is a green check mark, which is pretty fun to get, which means that everything is correct and everything is fine. And there is no initial state. There is nothing that a malicious actor can do to break your code, to break your assertion that you wrote in the CVL. Or you might get a violation. When you get a violation, it's a red X. It's pretty annoying. And what it means is there is some state with some inputs that breaks the property. And the prover shows us exactly what is that state and shows us step by step what happens and to help us to find the exact bug that breaks the property. So in this talk, we'll review some properties that we want the Aave token to have and see how to write them in CVL and what the results that we get when we run them on the Aave token code. And later, of course, also the governance. Okay, yeah. So first, before we start writing properties, we need to think, what even do we want the code to have? What properties do we need? And as Ernesto said, it's an ERC20. So first, we will need some simple ERC20 properties. For example, the transfer function, as in any ERC20, we would expect it to preserve the sum of the sender and the receiver, the sum of the balances. If I have some X tokens, X Aave tokens, and Ernesto has Y Aave tokens, and I transfer him my entire amount, the sum before the transaction is X plus Y, and after it should always be X plus Y. It can't be greater than it can't be less. Because if I transfer him tokens, then tokens shouldn't disappear and shouldn't create out of thin air. Also, we would expect, for example, that the sum of all balances of all of the users should be less or equal to the total supply of tokens in the system, which I think it's a pretty good property. And also, a user can transfer more funds than they have than their balance, which also it's a pretty simple ERC20 property. And to be more specific about the Aave token, there are more properties that we have, such as the delegate function, that we want that it will delegate the power correctly between users. If someone delegates their power to someone else, it should decrease the first user, increase the delegatee, and shouldn't influence any other user. So there is no this hidden address that might steal part of your voting power, or someone that you steal from some specific address. And because we run on all possible states and all possible inputs, we know that there is no edge case specific address that might do any of those things. So this is a CVL rule, which describes the first property. The sum should be preserved when we transfer tokens, the sum of both of the user's balances, the sender and the recipient. So let's go over it and see what's here. So first we have, on the first line, we have the name of the rule. And we have two parameters, the address 2 and the U into 56 amount. The address might be any possible address in EVM, any value. It's not limited to anything. And also the amount. The amount is any possible amount, so that means that if there is this specific amount or specific address that breaks something, we go over all of them. So it can't avoid us. Then we have the n variable, which means that we start here from any possible state, any possible initial state, and the transaction that we will run in a few lines in the transfer can have any message sender, it can have any message value, any block timestamp, any block number, anything. So if there is some specific input that might break or we might miss, here we run on all of them, so we can't miss it. Then we save on the side the sum of the balances of the sender and the recipient, the message sender and the recipient, the two. And we call the transfer function. And then we just assert, then the sum of the balance, or the sum of balances after and the sum of balances before stays exactly the same. So this is a pretty simple rule, simple property that we would expect of any ERC20 to have this property. So, of course, we run this rule when development, and everything was valid. Wait, and this is what you get when you write a good property. You see the green check mark, everything is correct, everything is valid, and it's pretty, you can be happy that you proven it. After we do that, we integrate the spec with the CI. And whenever there is a PR from the development team, they just automatically run the rules on the new version of the code. And then we just verify again that the rules still hold. In some cases, it might not happen. And then we found we have an issue either with the code, with the new code, and then it means that something is broken there. So that exact rule was integrated in BGD Lab CI, among other rules, of course, but that specific one just broke recently on one of their PRs. And what happened there is that we noticed that there are red X, which is, of course, bad. Red is for bad. And we can see this violation. Let's just click on it. Okay, see red. And we can see here that this assertion broke. And the sum, here, this assertion broke is false, right? So here we have this assertion. The sum of balances before the transfer was 42, and after it was 44, which means that the sum of balances increased. When it happened, let's take a look on the side on the variables, and we can see that the two address here and the message sender here are the same, right? Yeah, they're the same. What it means, in the code, there was a bug that if someone send money to themselves, transfer money to themselves, they just get an extra money for free. So if this, in this case, the message senders transfer themselves amount 1, and they just got an extra 1 token. So it means that if this code was deployed, it wasn't, but if it was deployed, then anyone can just gain infinite amount of Aave token. They have to have at least 1, but then they can have as much as they want. They can just double themselves forever, which is a bad thing might happen, especially in a governance token. And of course, after the fix, we can just rerun the rules and then get the green check mark again, and then we know that it doesn't happen anymore. Okay. Some other property that we have, they're more specific to the Aave token, to the governance part, is the integrity of Delegate. The Delegate function, what should happen there is that we have A delegates to B. We expect that A's voting power will decrease, B's voting power will increase, and all other users shouldn't be influenced by this delegation. Because if A and B haven't been delegating to anyone previously, then the fact that I am delegating to someone else, that I haven't been delegating to anyone, and the fact that I haven't been delegating to anyone, and then I start delegating to him, no one else would receive or lose voting power because of that operation. So let's see how to write a rule for that, how we will go over it. It's a bit long, but we'll go over it part by part and see exactly how simple it is. Okay, so in the start we have Alice, Bob, and Charlie, A, B, and C. So Alice, Bob, and Charlie can be any address. As I said before, any possible address can be there. So we can't miss any edge case if there is a specific, a specific address that might break something, a malicious actor or something. It also go over all of them. So especially that also. So it's unconstrained. Then we start from any possible state. We want that Alice will be the message sender of the transaction, because later here we see that we call the delegate function and want Alice to initiate that transaction. Also, we want that Alice, Bob, and Charlie will be different than one another, because Charlie is the one that represents the third-party user who doesn't know the wizard, doesn't know anything, and just shouldn't lose or gain anything from this delegation. And Alice and Bob can be the same person, because if someone delegates to themselves, it doesn't have a meaning for our rule currently. And then we expect that Alice and Bob don't delegate to anyone. This is this part, the bottom require. That is Alice delegating to someone, or is Bob delegating to someone, we require that they don't delegate to anyone. Then we just save some data on the side so we can compare it later. We save the Alice's balance, Bob's balance, and then we save the Alice voting power, Bob's voting power, and Charlie's voting power. And later we will have the assertion on it, so we need currently to save the data before so we can compare it later. Then we call delegate with one specific requirement, that Alice is the message sender. Alice is the one that's initiating this transaction, but the message value, specifically here because it's an unpayable function, the message value has to be 0, but the message value, the block number, the block timestamp can be anything. So if there is a specific, maybe there will be a specific time in which something will break. Even all of those cases we cover, because it's unconstrained, it can be anything. And then after we call the delegate function, the solidity delegate function, then we again save the Alice, Bob's, and Charlie voting powers, and we check 4 assertions that if one of them break, we have a counterexample, we have something that broke. What we expect is that Alice's voting power will decrease, Bob's voting power will increase. We expect also that Bob will be the delegatee of Alice, that is another function that we have in the Aave token, that who is your delegatee, would you give your voting power to, so Bob should be the one. And that Charlie didn't lose or didn't gain anything, so Charlie's voting power stays exactly the same. So when we run this rule, let's see what happens, right? Should pass. But it fails. What failed here? Let's check which assertion failed. The third assertion failed. Here you see there is false. Here. The one that checks that Bob is the delegatee of Alice. Why it failed? So we can check here the rule parameters. We can check here on the side that Bob, in this example, is 0. Why is this important? Because in the Aave token, whenever you delegate to 0, it's a special address. Whenever you delegate to 0, then it means as if you delegate to yourself. So although you're not delegating to yourself, from the system perspective, you are delegating to yourself. So Alice's delegatee is herself. So then Bob is not her delegatee. So that breaks, which is not good. It means that we missed this edge case when we wrote the rule. We should have prevented the system from even prevent from the prover to even think about this option. So what is missing here? So what do we miss in the beginning? What should have we required? We should have required that Alice, Bob, and Charlie are not 0, because if there was a 0 address, we know that 0 address can initiate transaction, they can't vote, they can't do anything, so it doesn't even make sense that Alice, Bob, or Charlie will be 0 address. So when we require it as following, then the rule verifies and everything works. We get the green check mark. Yeah. Where? Because if Alice was the 0 address, then technically it doesn't break. This example can't happen because we know that Alice, Bob, and Charlie are not the same. So if Bob needs to be 0 to break the code, then we already required, if Bob is 0, then Alice is for sure not 0, and also Charlie. Okay, so to prevent this counterexample specifically, this case that we know that is incorrect, we don't need to require that Alice specifically is not 0, but because we know that this case is not interesting for us, and we can see that, oh, so when it's 0, something breaks, and we know already that it's not an interesting case, so we prevent those cases from even turn up because we know that they are unfeasible cases. So we just prevent them, let's say, in advance, because we know it's a safe assumption. Okay, so those are 2 examples on the Aave token, and now let's go to the governance v3. Let's see how we can use CVL to improve the security in governance v3. So let's review some of the properties that we want the governance v3 to have, and see how to translate them to CVL and run them and see the results. Okay, so so which properties would we expect the system to have, the governance v3 to have? We have an invariant, then invariant of the system that if a payload doesn't exist, so it's greater than the payload counter. Ernesto said before that there are payloads and they live in some other chain. And we have a payload counter that states how many proposals were created up until now. So any payload ID which is further than the counter, so doesn't exist yet, should have a null state. There is a struct of the state of the proposal, and the state should be null because it doesn't exist yet. So it doesn't make sense that it won't be 0, it won't be null. So let's see how do you do it. But first, we need to understand what are invariants, how do we prove them. So what are invariants? Invariant is a property that should always hold. In some tokens, it might be that, let's say, the balance of 0 is always 0 because they prevent transferring and minting to 0. In this case, I want the invariant that for any proposal ID that doesn't exist yet, we want their state to be null, to be 0. And how do we do it? How do we prove invariant? So what we do is we do an induction. So we have the base of the induction that we call the constructor, and then we check whether the invariant holds or not. So if the invariant holds after the constructor, then we have the first step because we have the base of the induction. Then what we do is we start from any arbitrary state, but we require that the invariant, the condition, was already true. And then we call any function with any inputs, any possible function, any possible function that the contract has, and we give it all possible inputs that might happen ever in any message sender, any block timestamp, let's say they have 4 parameters, 2 addresses, 1 uint and 1 bool. We give it all of the inputs, all of the possible inputs, and then we check that we assert that the condition is true again. So after the function that it's true again, and if it's true again, then we know that whenever we start with the invariant being correct, we will end up at the end at the invariant being correct again. So because we know that at the base of the induction, we know that it was correct after the constructor, and then we have proven that whenever it was correct, it will remain correct after any function with any inputs. That means that it's correct forever, because we start from it being correct after the constructor, and then no matter what we do, it keep being correct always. So now we can assume that it's correct because we're proven that it's correct always. So no matter what, we can assume it. So why I'm explaining this to you? Because now we can understand what is the meaning of this statement. So this is an invariant that represents exactly this property, that non-existing payloads have a null state. The non-existing part is here because let's start with the invariant keyword. This is the type of the first it was a rule, now it's an invariant. And then this is the name, and then you have the uint40, the ID, the payload ID. So if the payload ID is greater than the payload count here, the left-hand side of the statement, that implies that the payload state will be none, which is pretty simple way to show, to prove that no matter what, there can't be, let's say, any payload that's in the future that will be allocated next or sometimes in the future. It can't be already initialized with something. It should always start with none, which makes sense because none is the enum of 0. So in EVM, usually it will start as 0 from the beginning, but here we can prove that there is no way to backtrack or something. So this invariant we proved it, and now we can use it. What do I mean? When I say use it, what do I mean? I mean that for the next rule, we will use the invariant, we'll require the invariant and see that it helps us to prove the rule. So another property that we want to have in the governance v3 is that whenever a proposal, as Ernesto said, there are a pretty complex state machine for the proposals. They have the non-state that I showed before, we have the created, we have the active, we have the queued, executed, we have also canceled, and we have expired, a lot of states. And the state machine is pretty complex. But we want to describe a simple property that covers many, many cases, and not just have a lot of tests that checks when I start in this case, and then I call some function, some specific function with some specific input, it doesn't break. Yeah, but I want to prove that no matter what, if I get to the canceled, expired, or executed states, I can't go out from that state. It's a terminal state. So whenever we go in, we cannot go out ever, not even to one from the other. We can't, if we get to canceled, we can't go even to expired or executed. We're just stuck there forever. Same as for the expired or the executed, which makes sense. Let's say that we have some proposal that says, let's pay from someone. Let the DAO decide to pay for someone, and then that proposal is executed. We don't want there to exist any function with any input that somehow can make that proposal to be not executed yet, which is called queued, and then you can just pay them again. It's not a good thing that happened in DAO. Also, if you have some proposal that's expired, and we know, oh, that is expired. We know that it won't happen in the future ever because it's expired. So let's say maybe there is a proposal that that says let's pay for someone and it's expired. So we will just create another proposal that we will actually pay them, and then we execute it. So we pay them. But then let's say that there is some way to make it unexpired, the first one. So then we can make it unexpired, then pay them again. So that also doesn't make sense. So we want those states to be terminal. If something happened, we want to be sure that we can't leave those states. This is why this invariant is so important, and it came up while discussing with BGD about what they expect the code to hold, and this is one of the invariant we came up together, one of the properties we came up together. And let's see how do we write it in CVL. So this is a parametric rule, which is before we saw a specific rule with the delegate and a specific rule with the transfer. We had one function, one specific function that had any input. We started any possible state. We called a specific function and with any input, and then we saw that the assertion passed. Then we had an invariant that starts in any possible state, and then it called any function with any input, and then check that specific condition holds still. Now we have a parametric rule, which we start in some state, in any state that the requires are correct about it. Then we call any function with any input. So again, any external function or public function that the contract has, we can call it, and then we can run the assert and be sure that the assert always holds. So here we start with method f. This part is the parametric function here. Okay. So the method f can be any function. The args represent any parameters, and we have the uint40, which is the payload ID, and we require invariant, which means that we tell to the prover, we say, okay, so we've already proven this property. We know that if the ID is greater than the count, then it means that the state should be none, which help us to prove it, because without this invariant, this property can't be proven, because for a specific example, that let's say that the next proposal ID, the next one, the one that we will define right now, will start somehow without this invariant as expired or as canceled, and then we propose a new proposal which go over this proposal. So then its state will become created, which was canceled before, and then it become created. So we left the canceled state and we entered the created state, which doesn't make sense because it shouldn't happen. So the way we prevent those cases is by proving that it can't happen and then requiring it. So now we know that it doesn't happen. Next, we have the require. This require is exactly as I said before. We need to start in a state in which the state is either executed, canceled, or expired. And if we started in that state, it's one of them, then we call any function with any parameters, any message value, any block timestamp, block number, message sender, anything. So there isn't, let's say, a hidden bad actor, a hidden address that has the authority to do whatever he wants or to somehow roll back transaction or proposals. It checks everything, so any message sender, anything. And then we just sample the after state, and we assert, does the state before equal to the state after? This is a pretty simple rule after we go over each part of it and see that they are pretty simple. Here we just define the state. Here we require the invariant that if the ID is greater than the count, it should be none, and then that we start in a state in which it's executed, canceled, or expired, and run the function, and assert that it's the same. So after we do it, we get a violation. So this is a violation. Let's go over first the green parts, which are the good parts. So for all of the functions that you see here that there's a green check mark, it means that we were able to prove so no matter what initial state we had and what parameters we put in to any of those functions, the cancel payload, the get payment payload state, any of those functions, no matter the input, the assert didn't break. But for the function update executors, the assertion broke. It went from expired to queued, which means that there might be a case in which we have an expired, we have a proposal which is expired. Then we call this function. There are some inputs to this function that will change the state from expired to queued, which means that, as we would assume, at least I think it's reasonable to assume that if a proposal is expired, if a payload is expired, it means that we can't run it in the future, right? That is the meaning of expired. Let's say you have milk in the fridge and it's expired. You assume that it can't be unexpired and then you can drink it again because it's expired already. But now here we see that it might be unexpired and makes it to be queued. With queued means that someone can run it and execute it, which is not good for the system and not good in general. Okay. So what we learned today? We learned that what CVL even is. So it's a language for developers, that it's already like that we can write rules in an intuitive way that will help you secure your code. The values that CVL gives you is exhaustiveness and finding bugs, that we can check all of the states, the exhaustiveness part, and finding bugs we saw from the CI integration, that whatever you do, if you integrate it in your CI, the rules run again on your code, on your new code, and you can know for sure that no matter how many small changes you've made, even if you change one function, one line, one if statement, something might break. So then after the rules run over it, you know that there are no initial state, no inputs to any function that will break those properties. And you know that is correct. This is why you should integrate CVL into your CI. And we also saw how CVL rules and CVL invariants look like. And the reason I'm saying Solidity so much because they look pretty much like Solidity. They are pretty similar. Thank you. Any questions from someone? Yes.
Does the prover support a reasoning about large multi-contract systems as a single state?
Okay, so as long as it's on one chain, then you can have a large state of multiple contracts. Yeah, you can have it. The initial state will have any state of all of the contracts, so any one of them can have any state. And then when you call functions between them, then the contract will interact with one another and influence the state of one another if the functions should do it, of course. And then, yeah, it works. Anyone else? Yeah.
Hi. How you handle with timeouts, and especially timeouts with, for example, division?
Can you say again?
How you handle with timeouts when you run rules and got timeouts?
Yes, so also we can get timeouts, of course. It's something that might happen. So if we have a timeouts, there are two options. Either we try to have more more invariants, require more invariants, so the state will be more simpler for the prover. So let's say that you want to prove something, there are a lot of possible states, but if we have many invariants that, of course, they are correct, then it will narrow out the possible states, the realm of possible states, but still only the valid states. So that helps to narrow out some of the possible inputs and make the prover run faster and prevents timeouts. And also, if let's say all hope is lost and you try to write all of the invariants that you can add, you can also summarize some functions, which means that you can use, I didn't touch that feature, but you can also take a function, a Solidity function, and replace it with CVL implementation or CVL, a CVL implementation of that function, which will run faster in the prover, and then it will make the timeout from the division or from something else to have less likelihood to happen. Any other questions? Okay, thank you a lot.